Okay, welcome everybody to the physics seminar this week. Rizwana Jani se case liye zimmedari mujh pe hai. So it's a pleasure to introduce Omer Malik, who's going to talk about percolation theory. And Omer did his BS from LUMS in EE in 2013. And then he has a very interdisciplinary background. He went to do his MSc in nanophysics in 2015 from Belgium, and then he shifted to Rensselaer Institute, from where he did his MS in CS, as well as his PhD in physics. So it's a pleasure to have him here, and currently he's serving as an adjunct faculty member in the mathematics department. Right? And before that, I guess he was in Wells Fargo.
Yeah,
as a quantitative analyst.
Yes. Thank you, Dr. Saman, and thank you for inviting me to give this talk. So I'm going to be talking about some recent work that I've been doing with some collaborators on concurrence percolation theory. And concurrence percolation theory, the goal of it is essentially to develop a framework to study the critical properties of quantum networks. So in this talk, I'm going to start by talking a little bit about quantum networks and why we can't use classical percolation theory to analyze them. And then I'm going to see how concurrence percolation theory is able to overcome the limitations of classical percolation theory in analyzing the critical properties of quantum networks. And then, up till now, concurrence percolation theory has been defined for pure states. So we're going to see how adding noise to the quantum network, how that changes the theory. So, I'm going to talk about the development of mixed state concurrence percolation theory and show how its results differ in some very surprising ways from the pure state case. So yeah, let's get started. So a quantum network refers to a network where the edges between nodes represent shared entangled particles. So as we can see in this diagram, the nodes you can think of as, if this is meant to be a model of a communication network. So we can think of the nodes as, labs where we have multiple particles, and each link represents an entangled particle that is shared between nodes. And this is meant to model a communication network that is built upon quantum teleportation, right? And this kind of network is supposed to have advantages in terms of security and the ability to transmit quantum algorithms. So it is of interest as studying it as a model for a hypothetical quantum internet of the future. So the thing that we are limited by is that the entanglement that exists in these links, we cannot just assume that we will always have perfect entanglement, that we will always have maximally entangled pairs. Because to create a maximally entangled pair, that takes more resources than to create a less entangled pair of particles. So entanglement is a resource. And what we, in a quantum network, what we want to do is that we want to use the minimum amount of entanglement that we can get away with. And what we mean by that is that in order to communicate between nodes, we have to convert those non-maximally entangled pairs into maximally entangled pairs. And we want to ask, what is the minimum amount of entanglement needed to ensure connectivity in the network, right? So the process of converting a non-maximally entangled pair into a maximally entangled one is a probabilistic process. It has some probability of succeeding and some probability of failing. And what we want to know is that, picking any two nodes in this network, like this one and this one, what is the smallest amount of entanglement that we can start out with that will still allow those nodes to be connected. after we have converted each non-maximally entangled pair into a singlet. Now, if you are familiar with it, this will immediately remind you of the, how we define classical percolation, right? So in classical percolation, we have a network or a graph or a lattice, and there is some probability of nodes being deleted from the network. And then we are able to calculate the minimum threshold on the probability such that a cluster still exists in our network. So a natural way to answer this question, to answer the question of what is the minimum amount of entanglement needed, is to use the methods of percolation theory, right? And that's like a very well-developed theory at this point. So if our network, for example, represents a honeycomb lattice, if this is our quantum network, then we know what the percolation threshold of a honeycomb lattice is, right? That is a known studied problem. And then we can say, well, that threshold tells you the minimum amount of entanglement you need in order to ensure connectivity in this network.
What is percolation theory?
So percolation theory is just the study of essentially the problem that I'm describing, right? It is, you take a lattice and with a certain probability, you delete edges from it. You can also delete nodes, but for our purposes, we're talking about deleting edges from it. And then you study the clusters that form, and you can see that as the probability of deleting a node changes, there is a phase transition. So below that phase transition, when the probability of deleting nodes is low, you have a giant cluster. You have a cluster that connects the entire network, an infinite cluster in an infinite network. But after that phase transition, when the probability of deleting a node gets higher, you don't have that giant cluster anymore. You just have small disconnected islands. And the threshold value at which this happens, it's a function of the topology of the network. So for 2D lattices, it is 0.5. For honeycomb lattices, it is like some function of sine. I think it is like 0.67 or something. So it is a very well-studied problem.
Classical.
Yes. So you take a network, delete certain nodes. And as you change the probability of deleting those nodes, you observe a phase transition. So it is essentially the problem we're talking about, right? So we can say that, we can use, we have all of these results from percolation theory. Given a topology of a network, we can answer the question, what is the probability of edge deletion here, which will still allow us to have a like a connected component in the network, which will still allow connectivity in the network.
So we are saying converting a honeycomb lattice to.
I'm actually
angular
getting to
lattice.
that. I'm actually getting to that. The picture is a little bit ahead of what I'm talking about. So the problem is that on a quantum network, we can change the topology of the network, right? So a honeycomb lattice has a given percolation threshold, but by performing an operation called entanglement swapping, we can convert the honeycomb lattice into a triangular lattice, which actually has a lower percolation threshold than the honeycomb. So in a classical network, we can just take the honeycomb lattice and answer the question of like what threshold we need for the connectivity strength. But in a quantum network, any given network may be transformed into another network, which may potentially have a lower percolation threshold. So in attempting to answer, what is the minimum connectivity we need, it becomes a much more complicated question. And in general, it is very difficult to determine if there is a particular pre-processing strategy which is optimal, right? So it is difficult to determine if we have finally converted our network to one which will have the lowest possible percolation threshold.
So triangular lattice has the lowest possible, is it?
No, it doesn't have the lowest possible. It just has a lower one than a honeycomb. So this is just an example of that, right? That we can convert the honeycomb into a triangular lattice, right? And in general, especially if we start talking about random networks, right, which aren't so, which don't have like a nice regular structure, it becomes even harder to determine what type of, if the threshold that we're calculating is optimal, or if we can do some entanglement swapping and end up with a lower threshold. So concurrence percolation theory is the attempt to answer this question. So concurrence percolation theory calculates the concurrence for the entire network. Now, the concurrence is a measure of entanglement, and we'll look at it in a little bit. And basically, if we want to know, if we want to establish the connectivity strength in a network between two nodes, let's say S and T, for classical percolation, what we would do is we would look at, the paths that remain in the network after the, non-maximally entangled pairs have been, some of them get turned into maximally entangled pairs and some of them do not. And then for the, and then we see what is, if we have certain connectivity between nodes S and T, right? So we establish this probabilistically. But with concurrence, we calculate the total concurrence as a function of all paths that connect S and T. So it is not a probabilistic outcome, it is deterministic. It depends on every single path that connects those two networks, and we do not take into account converting those links into singlets, into maximally entangled pairs. And then we can look at a threshold on the concurrence, and we can ask what is the minimum concurrence of each link to ensure connectivity in the network. And as if this is unclear, I hope it becomes clearer as I'm going to talk about the theory a bit more. So I hope it becomes clearer as we go on. So concurrence is one of the reasons that it is very effective is that for a lot of states, it can be written in a very simple way. So let's say this is the state that represents any given link in the quantum network, where we have these, the entanglement is effectively determined by this parameter theta, and this is our state. So we can see that when these values are equal to 1 over square root of 2, we will have a maximally entangled state. And for other values, we will have a non-maximally entangled state. So let's say that, in this example, like let's start at the bottom here, we want to find the concurrence between this node over here and this node over here. So what we do is we start essentially applying certain protocols, which are which we're going to look at, in order to calculate. We slowly remove nodes from this network until we have established a direct link between the source and the target node of interest. So over here, we see that this node has been removed and its links have been shunted off to other parts of the network. In this, it's a little hard to see, but we have two links between these two nodes that have been converted to a single link. Over here, we see that we have this triangle, and this node has been eliminated, and we've established a second direct link between these two nodes. So essentially, to compute the connectivity between two nodes, we reduce all nodes to establish a direct link between the source.
And we are doing it by entanglement swapping?
Yes. So we are doing it by entanglement swapping and entanglement concentration. So entanglement swapping allows us to entangle nodes that weren't previously entangled, but were connected by a chain or had an intermediary node. And entanglement concentration allows us to convert multiple weakly entangled links into a single strongly entangled. Okay, so we can look at these procedures. Entanglement swapping, it's best understood if we look at this simple scenario. Let's say we have 3 nodes, A, B, and C. And A and B share an entangled pair, and B and C share an entangled pair. And then node B performs a measurement known as a Bell state measurement on the two particles that it has, that it shares with nodes A and C. And this will cause nodes A and C to get entangled with each other. And I talked about a Bell state measurement. So if you're not familiar with them, these are the four Bell states. And a Bell state measurement is just a measurement in the basis of these states. So this is just like a partial, it's a measurement by one of the projectors. So if these are our two states, right? We just have the state A, B1 between A and B, and B2, C between nodes B and C. Then if we apply this projector of one of the Bell states in the basis B1, B2, we will end up with a situation where the particles of A and C will become entangled, and they will both lose their entanglement with the particles of B. So we will have four such outcomes corresponding to each of the Bell states, but they will all result in A and C becoming entangled with each other. So this is known as entanglement swapping, and it allows us to, entangle previously unentangled nodes. Now, if we look at the concurrence, so, we have some concurrence associated with A and B, like there is a concurrence for this link, a concurrence for this link. We can write the resulting concurrence of A and C as a product of the concurrences of the original two links. So it combines very nicely, just as a product. And if we have multiple links, right? If we have A, B, C, D, E, F, and then we do a series of these measurements, right? You can imagine we have another node here, and then C does a Bell state measurement, which eventually causes A and D to become entangled. We can repeat this process, and the concurrences in series just multiply together. So that was the entanglement swapping portion, and for entanglement. Yes.
Just clarification. So we are assuming that the nodes are multi-level quantum systems, because if they're qubits, then the total entanglement would be restricted.
No, I think I don't think we're assuming necessarily that they're multi-level entangled systems.
So qubitical.
There's a monogamy of entanglement that makes sure okay, अगर वो pairs increase with each other, then the total is fixed. So यहाँ पे तो जैसे the total entanglement C series can be n as well, because individual CIs can be one if they're not qubits, if they're allowed to be multi-qubits. So then we can go to n, which is okay. I'm just asking, like, what's the setting? Are these nodes only qubits, or they can be multi-qubit systems?
So I mean the nodes the nodes are only qubits. Now what we can have is that we can have a node can possess multiple particles that it shares with other nodes. So
I mean, one node can have more than one qubits.
One node can have, yeah, it can have more than one particle. Yeah.
So as a whole, the node is a multi-level system then.
Yeah. And I think when we look at the concentration scheme, where specifically we have two connections between nodes, that you can model that as not as a qubit, but effectively as a system with 4 levels.
Right.
Yeah. But I think we haven't looked into the possible restrictions that you're talking about.
And there's a principle called the monogamy of entanglement.
Okay.
That if you have only qubits, and then the total entanglement cannot be more than a threshold, and it doesn't matter the number of the nodes.
I see.
लेकिन आपके केस में तो जो total entanglement है measured by C series, it's function of the number of nodes, which mean that the nodes have to be multi-level systems.
Right, right. I think they are effectively.
मल्टी लेवल सिस्टम में होगा तब भी तो कोई बाउंड आएगा 3 लेवल फॉर एग्जांपल
हाँ, लेकिन उसमें वो बाउंड फिर वो level
ऊपर हो जाएगा ना वो तो ऊपर हो जाएगा right?
Yeah, so
लेकिन हमेशा बाउंड होगा कोई ना
बिल्कुल
they are effectively multi-level systems, yes.
तो जो entanglement है वो तो बाय पार्ट है
आपका आर्गुमेंट
Yes,
भी
the
अप्लाई
entanglement is bipartite.
क्योंकि ठीक है सपोज करें वो क्यूबिट्स इस्तेमाल कर रहे हैं 3 लेवल सिस्टम बाउंड ऊपर चला गया लेकिन इफ ऑल ऑफ देम आर क्यूबिट्स अगर आप नोड्स इंक्रीज करते जाएं फिर वो बाउंड को वो एक्सीड कर जाएगा तो मतलब इट मस्ट बी अ फंक्शन ऑफ समथिंग एल्स एज वेल राइट इट कैन नॉट जस्ट बी अ फंक्शन ऑफ
नहीं, लेकिन जो आपने शुरू में नेटवर्क दिखाया था उसमें तो एक नोड पे कई क्यूबिट्स थे ना तो एक सिस्टम मल्टी लेवल होने की
नहीं,
बजाय
वो nodes का अगर तो मतलब
क्यूबिट्स हैं
Yeah,
है ना
there's multiple
क्यूबिट्स
qubits.
थे
Yes.
हाँ
ठीक है तो अगर नोड अगर n के साथ साथ क्यूबिट्स भी इंक्रीज हो रहे हैं फिर तो नहीं बाउंड वो सेपरेट
Yes, and to clarify, n is the number of nodes, yes, and well, n is the number of links, so this would be for n plus 1 nodes, yeah. Okay, so the second protocol involved is entanglement concentration. So in this case, we have more than one link that is shared between nodes. So we have more than one pair of particles that have been shared between nodes. And here we utilize the sort of well-known Nielsen's theorem, which guarantees that if one state majorizes another, we can transform that state into the other state. So if we look at the joint state of these two links in parallel, we can just write them like this, and then we can show that by Nielsen's theorem, this state can be converted into a state of this form, where this is, effectively just a single link where the new parameter theta is related to the old parameters like this. And then if we calculate the concurrence of the new link as a function of the concurrence of the old link for two parallel links, this is the expression that it has. It's a bit more complicated than the series expression, but it still generalizes nicely to multiple links in parallel. So we've essentially ended up with rules for calculating the effective concurrence between any two nodes in the network. So the pros of concurrence percolation theory are that it is deterministic and it is optimal. And what we mean by optimal is that it will give you a lower threshold than any that you would determine by doing some kind of pre-processing strategy and then using classical percolation methods to analyze the network. The cons are it is difficult to calculate because you essentially have to calculate it for every path in the network. So for certain networks, and we're going to talk about the Bethe lattice a lot, we can write down analytical expressions for it. And so we can write down the analytical expression for the threshold on the Bethe lattice, which is 1 over the square root k minus 1, where k is the coordination number of the Bethe lattice. And if you're not familiar with it, it is just a lattice where each node has k connections, one to its parent node and k minus 1 to the next layer. And then each of those k minus 1 nodes have k minus 1 further connections. So you can imagine it as a tree where it expands by where each node has k minus 1 branches coming out of it. Okay, so and for networks that aren't regular, for complex networks, we can develop approximate methods to speed up the calculation. Okay, so that was just like a very quick overview of concurrence percolation theory. So far we've only discussed pure states, right? But in the presence of noise, we would get mixed states, which are statistical mixtures of pure states. And of course, if we are looking at a real communication network, we expect to have noise. So we want to generalize concurrence percolation theory to involve mixed states. And there's different types of noise that we could encounter. And this is a typical way that we will be looking at our state in the mixed state case. So we can have bit flip noise, where if this is our desired state, we can get that with probability f, and then we can get a state where one of the particles has its state reversed with probability 1 minus f. We can also have phase flip noise, where one of the particles has its phase flipped, or we could have the more general type of noise, depolarizing noise, where we have our original state mixed with probability x with just white noise, which is represented here by the identity matrix. So essentially, our recipe for trying to construct mixed state concurrence percolation theory is going to be to see if we can write down a series rule based on entanglement swapping and a parallel rule based on some criteria for transforming states into each other. But the difficulty that we envisage is that for mixed states, in general, you will not get a nice closed form expression. If you do entanglement swapping, you will not get a nice closed form expression the way we got before, where it was just the concurrences very nicely were just the product of the individual concurrences. And for the parallel rule, in the pure state case, we have Nielsen's theorem, which essentially guarantees that we will be able to find a transformation of one state to another. But mixed states do not have unique representations, right? And that means that it is, in general, to transform one mixed state into another, you're not able to do it. You have to essentially optimize over the entire ensemble. It is like an NP-hard problem to establish that kind of convertibility. I think it is in fact an open problem. It is not something that's been solved. So what we will do is we will focus on bit flip errors. And this is what our state is going to look like. With certain fidelity, we are going to have the desired state, and with 1 minus f, we're going to have the error-prone state. Now, if we write out this matrix, you will notice that it has this interesting form where it only has entries on the diagonal and the off diagonal. And this is an example of an X state. And all the Bell states are also X states. So X states, the fact that our state can be written like this simplifies some of our calculations because X states are closed under multiplication, right? So entanglement swapping is essentially, multiplying these matrices, and we will stay within the space of X states. So the concurrence for an individual link is again has a nice sort of like simple expression.
Yes. One quick question. So let's say you have 2 qubits, and for entanglement you are assuming like 2 qubits, and then you have 4 Bell states.
Yeah.
And the bit flip model that you have written is not the usual bit flip. In the usual bit flip, like we have 2 qubits, and we assume that the 2 qubits are independently undergoing bit flip noise. आपका जो bit flip noise है वो ये है कि you are not flipping, you're not, क्योंकि उसमें है कि qubit है, and 0 में either you go to 1, 1 में either you go to 0.
Yeah.
अब यहाँ पे आपके पास 4 Bell states हैं, and in the what you are probably doing that you're flipping. Your channel is like either you have the same state 5 plus, or your state goes to another state psi plus, not the other 2 Bell states, right?
Yes.
So it's just like very special bit flip. It's just not a general bit flip.
Yeah, I guess my answer to that is that in two parts. The first is that we are looking at more general noise. The second thing is that I think,
Like other than this presentation, you're looking.
yes,
Okay.
yes.
Okay. So like this is special.
This is a specialized case, and I think part of it is that you try to find, if you try to find a problem that has a tractable solution.
Yeah, I understand that. You know,
Yeah.
That's totally okay. I mean,
Yeah.
I also, do this kind of work, so I know.
Yeah.
You come up with a model that you can solve, not
Exactly.
that
Yeah.
the model that
So this is
जो असल वाला नहीं है।
no, this is admittedly not the most general noise that you can have. It is a specialized thing, but
in this case is special jarring क्योंकि आपका जो psi plus है और फिर phi plus है, and both of them are Bell states. Basically आप both constraint कर रहे हो basically noise के effect को।
yes,
कि आप वो entangled states के बिल्कुल maximally entangled states के subspace में basically आप रह रहे हो।
yeah.
असल में noise तो पहला काम तो ये करेगा आपको उस subspace से बाहर फेंक देगा आपको।
Yeah, I think that like the way I would justify it slightly is that you can have I think that the ability to first transform whatever noisy state you have into a Bell state, for example, like that will just, you can treat that as separate from the rest of this, like looking at the rest of this. So, this is sort of like zooming in on one part of the treatment. So,
लेकिन अगर आपकी noise कम हो तो you can take single qubit noise, no? And then it will be like
कम हो या ज़्यादा हो, like usually bit flip means that each qubit is undergoing an independent bit flip with a certain probability. But here the channel is like that even to have this channel, अगर आप कोई खुद से process construct भी करना चाहे, it's actually a very hard problem to implement this channel itself. Like because nature wouldn't easily be in, doing a noise like this, that one Bell state is going to another Bell state automatically with a certain
right.
probability.
And there is one other aspect, which is that the protocol that we're going to be presenting, not the protocol exactly, but what I mean is that I'm going to be describing the situation for this specific form of the bit flip noise. But if you also have phase flip, it works equally well for that. And then if you have mixed bit flip and phase flip, which will be like a more general case, it still wouldn't be the full depolarizing noise. It also works for that. So what you can show is that if you have phase flip noise, you can convert, it defined as this, you can convert it to bit flip noise. So even though this is maybe not what you would see, I think that if you can solve it for, if you can develop the concurrence percolation theory for this, I think those results also apply to slightly more general noise as well. Okay, so to continue, right, so now essentially we're just going to try to see what it looks like when we try to build entanglement swapping and like some equivalent for the parallel group. So we have two copies of this state with potentially different fidelities, and we just do a Bell state measurement to do entanglement swapping, and we can show that the resulting state is another state with the same structure. It is another bit flip state with fidelity that can be written as a function of the fidelities of the two original states. And we get the very nice result that the concurrence is once again just a product of the concurrence of the original links. So the series rule, very nicely turns out to be the same for this particular case as it does for the pure state case. But for the parallel rule, we can no longer just do a deterministic transformation between our, between two links in parallel into a new link with higher concurrence. we have to use a entanglement purification procedure, which will only succeed probabilistically. So this is the schematic layout of the procedure. I'm not going to go through it, but essentially our purified state, when we run it through this procedure, it has fidelity of this form. We do get another state that is a state with a bit flip error, but this is now the fidelity of the purified state, and it has a certain probability of success, which is given like this. So now,
But it is heralded, it is deterministic, eh? It is probabilistic, but it is heralded. You will be knowing when it is successful.
yes,
Yeah.
exactly, yes. So you will know that this particular procedure requires only a single copy, and you will know when it will succeed, and you will.
And what if it doesn't succeed? You have to throw away your whole network, or you have to start the verification again.
I think we talk a little bit about that, but we assume that you are able to reestablish the link and try again. So to begin with, that is what we assume.
Okay.
So this purification is happening between two qubits in particular, right? Between two pairs of qubits. And we are assuming that you can reestablish actually, we look at both situations. We look at the situation where we assume that it always succeeds. You have some resources to keep repeating it until it succeeds. But then we also look at the case where, well, what if it fails and it changes the network? So, and to answer your question, you don't have to throw away the network. You can just sort of like say, okay, those links are now vanished. So we'll see how we deal with that. Okay, so the concurrence for the new link can be written as a function of the concurrence of the old links in this way. And this also generalizes pretty nicely. So this summarizes the series and parallel rules for concurrence between our pure state and our mixed state case. This is how the parallel rule for the mixed state generalizes. So we have closed form expressions for both of them. So now we can just start looking at our systems, and a good one to look at is the Bethe lattice. But we have to remember that our parallel rule is now non-deterministic, right? So we assume we have resources, such as quantum memories, to store successful outcomes of the purification protocol. So essentially, in the next part of this, we are just going to assume that we have the resources to ensure that the procedure always succeeds. Okay, so this is what it looks like. And we show results for the Bethe lattice, the square lattice, and the honeycomb lattice. And in each of them, we're comparing the pure state case and the mixed state case. And we see maybe the somewhat surprising result that in each of these cases, we actually have the mixed state concurrence showing a lower threshold than the pure state concurrence. If we work out the exact expression for the threshold of the Bethe lattice, it is 1 over k minus 1 as opposed to 1 over square root k minus 1. And we see a similar effect for the square lattice and the honeycomb lattice.
How much mixed it is?
This is just a bit flip out.
What's F?
Oh, so F is over here. It is 2F minus 1. So C is equal to 2F minus 1. So F is equal to 1 plus C over 2. Yeah, so it is directly related to the concurrence. I'm just showing it in terms of the concurrence, but it is we're assuming that it is always greater than half on an individual link. And then I'm just reporting the result in terms of the concurrence.
So C is equal to 2F
minus 1.
minus 1.
Yeah. And
if F is 1, it should become 1, and at 1, shouldn't both be giving the same result?
They do. The dotted line is that's like a long story I don't want to get into.
Okay.
It's essentially a non-physical portion of the analytical result. But yeah, in all cases, it does converge as C goes to 1. Yeah. So this, I was assuming you're looking at this, right?
Yeah.
Yeah, this is because both of these are analytical expressions, they're not numerical. And this is just like a non-physical portion of the result, which I don't want to talk about in this presentation, but yeah. Okay, so like I said, we get a lower threshold with the mixed state. And whenever I say the mixed state, I just mean the bit flip state, than the pure state. But of course, the reason for this is that we have assumed that we have as many resources as we need to always ensure the success of the entanglement purification protocol, right? So now we want to look at. So first, this is the resource requirement, like quantified to some degree. So to make the purification protocol deterministic, we would need k-1 pairs of quantum memories at every layer, because at every node, we would need the ability to store successful outcomes of the state. And of course, this is a very steep requirement that would grow very fast with the network size, and it's not really physically feasible. So now we want to treat the purification protocol as probabilistic, and we want to model the effect of that. So essentially, we're going to look at the diluted Bethe lattice. We're going to say that certain amount of links are removed from the network. So we know the probability of purifying k of the links in parallel is given by this expression. And then we model the diluted lattice as, we take the coordination number k and we replace it with an effective coordination number, which is k times this particular probability. So in doing this,
we're throwing away the nodes that are the links that are where the purification is unsuccessful, right?
Yeah. So let me clarify slightly. What we're essentially doing is that we are replacing the coordination number of the Bethe lattice with an effective coordination number, which is like a non-integer number. So we have this. We have the ability to analyze the lattice analytically. So we are just replacing that k with this diluted value of k. So we are in the first instance, we are not actually like doing some kind of like Monte Carlo simulation where we look at actual lattices which have had their like links deleted. What we are doing is that we're just replacing k with an effective k, and then trying to analyze the resulting equations. And we can find a solution for the concurrence threshold. It shows like this very interesting feature where as k increases, the threshold first decreases and then begins to increase again.
This is very.
Yeah.
Where do these numbers come from? 2, 3, and 5.
So
is it? So the nodes are k, right?
The nodes are k. Yeah. Essentially, if you look at the threshold for the concurrence, you can write it in terms of an effective parameter. Essentially, what you're doing with the Bethe lattice is that at every layer, you are applying the parallel rule, and then you get a link in series which has a different concurrence than what you had before.
Mm-hmm.
So you have this like effective parameter that, and then when you take the series rule, you now have a new Bethe lattice, but with a slightly different concurrence at the bottom layer. So you can introduce this parameter which changes as you like essentially collapse the lattice slowly. The value of that parameter on the threshold is 2 by 3. That's where the 2 by 3 comes from. The remaining, I don't want to go into the calculation exactly, but essentially what we're doing here is that the expression for the concurrence is a function of the probability. And then you try to find a critical point for this by minimizing it, and you end up with these numbers. I know that's not a great explanation,
Right.
but that's the best I can do without going into the calculations themselves. Okay, so all right, so I'll close out here. So we extend concurrence percolation theory to the class of mixed states with bit flip noise. The series rule is the same as the pure state case, which is a product of concurrences of each link in series, but the parallel rule of the pure state case is replaced by a probabilistic purification procedure. It can potentially be made deterministic by incorporating quantum memories, but the number of memories required scale with the number of links in the network. So if we account for these resources, we see that our mixed state concurrence threshold is less than the pure state case. But without quantum memories, we get maybe the more expected result that the concurrence threshold increases for the mixed state case over the pure state one. So there's several things that we can still do. We've only looked at bit flip noise of a particular form. We can extend this analysis to more general types of noise, such as depolarizing noise, which is something I'm working on right now. The other thing is that, which Dr. Aisha brought up, which is that the network dilution scheme that we're looking at uniformly alters the topology of the Bethe lattice, because we are just replacing the coordination number with an effective coordination number. The process is, in reality, the process would not be homogeneous, it would be heterogeneous, right? Like different links would be deleted at every layer. So we would need to properly account for this, and that may change the threshold that we see. And finally, we see that because of the purification protocol, there is an interplay of classical percolation theory and concurrence percolation theory that we have not explored. What we mean by that is that now that the purification protocol has a probabilistic chance of succeeding, our entire scheme is no longer purely deterministic. So one aspect of this might be the reintroduction of pre-processing strategies, right? Because now we are again in the probabilistic regime. So now it once again might matter how we change the topology of the network prior to applying the purification protocol, which might potentially lower the final threshold. Okay, so this work has been submitted, and this is the title for it. We've submitted it in communication physics. Yeah, it's currently under review. So anyway, that's the end of my talk. Thank you for your attention. And are there any questions?
The quantum memories, how do you model them in your system?
We don't.
You said the results for both with quantum memories and without.
Yeah, so with quantum memories, essentially we're just assuming that the entanglement purification protocol always succeeds.
Okay.
So we don't have we're not modeling it anymore in any more of a sophisticated manner than that.
And you consider, when you compare for mixed and pure states, for the pure states, you also consider the memory as successful.
Well, the pure state case is entirely deterministic.
Okay.
There is no probabilistic element. So there's no need to introduce a quantum memory. There's no part of that can fail, essentially. Yeah.
I'm gonna show this one. Yeah, excellent.
Uh, Thank you all for,